So now lecture number 3, sum and direct sum. So sum and direct sum of module. Now we know what is sum and direct sum in vector space. So this is actually analogous. So just brief recapitulation. We know what is called left R module or sub module. We already discussed in the previous talk. Now let R be a ring and M and N are two left R module. Remember, it is left R module. We can talk with right R module also, but there is slightly some complicated notation in notation. So left R module is notationally it is easier to deal. Everything is similar, but notationally it is easier to deal rather than right module. Now we know this Cartesian product M cross N. So because M and N are two sets, so M cross N is again a set. It's a Cartesian product. It can be made R left R module. How can we make left R module? So first you have to we have to define the addition, because we need a commutative group. So the addition is in natural way. Natural way is just x1 y1 plus x2 y2. The x1 plus x2 y1 plus coordinate wise addition is vector space. Also we define like that. In every y we define like that. In coordinate also. So for every x1 y x2 y1 y2. Now this is by this definition. If I define like that, then obviously it is a commutative. It is associative because M and N are commutative. So commutative means x1 plus x2 is same as x2 plus x1, and similarly y1 plus y2 is same as y2 plus y1. So that's why x1 y1 xy1 plus x2 y2 is same as x2 y2 plus x1 y1. So an associativity and zero element is there, is 0, 0. Now next part is challenging. We have to define a scalar multiplication. So now A is from the ring. Now again this is just a scalar multiplication, same as like scalar multiplication in the coordinate system. So 2 into xy is 2x, 2y, like that. And obviously you can check easily that all the axioms of this left module. If it's a left module, we need some properties. So that some 4 condition or 3 condition. If one is there, we need to check 4 condition for multiplication and 5 condition for this addition. So this you can easily check. So that's why we can make that M cross N is a new module, is a module over R, like a vector space. Now this is called direct product. This is called direct product. Like a vector space, we have direct product. So the name sometimes is maybe confusing. Sometimes it's called direct product, direct sum. Or some book is called internal direct sum, external direct sum, internal direct product, external direct, something like that. Now internal direct product is not that. Basically they use 5 many different terms. One is called direct product, direct sum. What is sum, direct sum, direct product. Then internal direct product, internal direct sum, external direct sum, and external direct product. So 6 different terms. It may be confusing basically. Actually no, there is actually not 6 many terms. It's actually 3 terms. In different books they use different things. So 6 terms are like sum, direct sum, direct product, external direct product, internal direct sum, external direct sum. So actually there are 3 terms. We'll see what is the actual 3 terms. The other 3 terms is just a term in different terminology in different books. Now what is R2? If I take R as a ring over ring, the module R is a module over that ring R, then R cross R is a module like a vector space. F2 is a vector space. F cross is called F2. F2 is a 2-dimensional vector space over F for F a field, and we know F to the power n is a vector space over F, n-dimensional vector space. Similarly is R cross R. So R cross R is just a all set of all Cartesian coordinate like that. So order pair, x and y both from R. So we can make this as a module, like same thing, same definition. And this addition and scalar multiplication will be the same as in the scalar, the multiplication in the ring. No, not a new multiplication, just multiplication in a ring. What is Rn? Again, is n is for any integer. A natural number is Rn is just x1, x2, xn. x1, x2, xn ordered in R. So it is just by definition. And it's just actually the Cartesian product. It is A1 cross A2, A1 Cartesian product, A2 Cartesian product, A3 Cartesian product, An. There is nothing but the A1, A2, An small and A1 in A1 capital A1, A2 is capital A2, like that. So it is just definition of partition. Now question there is, what is R to the infinity? There is some little bit confusion. What is R to the power infinity? R to the power infinity basically is a sequence, set of all sequence. Set of all sequence. It is not terminate, it is sequence, such that every xi is in R for all I. For all I belongs to natural number union 0. Yeah, 0, no natural number. 0 is not there. So this is R to the power infinity by definition. So set of all sequence. So set of all sequence is actually R to the infinity. Similarly, it is R is now any ring, like it may be cow, dog. So if R is real number, say is a real number R. So if this is R, and R to the infinity is all real sequence. If C to the power infinity is all complex sequence, like that. Now we know that R to the power n basically is a polynomial with element its coefficient from R. That ring may be real number set, maybe complex number set. It may be any field. Now x1, x2, xn are like a coefficient. So it is just x1 plus x2, or if we start to say x0 plus x1 t plus x2 t square, something like that. So it is a formal. We know the formal representation of the polynomial is like that: 1 plus 2x plus 3x square, or 1 plus 2t plus 3t square. It is actually 1 comma 2 comma 3, in the polynomial ring. So it's basically the polynomial thing. Polynomial is the coefficient from R, the n degree polynomial. No, it is n minus 1 degree polynomial. Now, what is R to the infinity? R to the infinity is not a polynomial. It is actually sequence. It's a series, formal series, power series, what is called power series. Now, every element is actually the power is a power series, because you just add the 0, 0, 0, 0 in the last. So if it's 1 plus x, I can say 1 plus x plus 0 into x squared plus 0 into x cubed plus 0 into x to the power 4. So it is just 1 comma 0 1 comma 1 comma 0 0 0 0 0 0 0 0. It's actually null sequence. So the last thing is all zeros. Now this is not a set of all polynomials. The set of all polynomials is basically like that. It is a set union over all 0 to infinity, R to the I. And this is not same as R to the power infinity. It is a subset, proper subset. So any polynomial is a power series, but power series is not a polynomial. So 1 plus x is actually 1 comma 1 1 1. This is not in the polynomial. This is not the polynomial. This is not in this R to the power n. So what is R to the power in the union? That means is actually the sum coordinates are non-zero, and rest are after some time it is all are 0. So this is so a little bit confusing. So we actually define sequence like that. So this notation is maybe confusing. So we can define R square like that. Basically R square, we can thought this is a function actually. The element of R square is like a function. So better I say f belongs to R square is basically is a function from two element 0 1 say 2 or 1 comma 2, we can say 1 comma 2, first coordinate and the second coordinate to R, or maybe it may be any set, it may not be ring. By definition R square, say it is A, any set, abstract set. Now, how do you define this? So it is easy actually. Just the sequences, the ordered pair is just f1 comma f2. This is the corresponding ordered pair in R2. So if you know the function from a 1 comma 2 to R, that is the ordered pair. And if you know the ordered pair, we know the function. If the ordered pair is say cow comma dog, that means f of 1 is cow and f of 2 is dog. So function actually gives the ordered pair and the ordered pair gives the function. So it's 1-to-1 correspondence. So actually you can thought that ordered pair like this is a function from 1 comma 2 to that set. If it is S cross S, then actually the function from 1 comma 2 to S. So now R to the infinity is nothing but is any element of that is like a function from natural number to R. So if the sequence is A1, A2, that means the function from natural number to R, A1, A2, An are all in may not be real number, it is any abstract set. In the may not be ring, it's just a set R. Now just f of 1 is just A1, f of 2 is A2, the second coordinate. So clearly, so r to the power infinity, that means if it is 2 elements, so r square. Now we can define r to the power I. I is any index set. It may be finite 0, 1, 1 to 3, or 1 to 5, or maybe natural number. Is basically if any element from r to the power I is nothing but a function from I to r. It's a collection of all functions. So it is set of all functions such that function from I to r. Any function. No need of is nothing continuity or injective is there. So because there is no topology now, there is no condition of question of injectivity, or no question of is continuity. Injectivity is the question is there. This is just a set property. No, this I may be anything. I may be a say q. So q to r. So I to the power r to the power q means it is a set of all functions from q to r. So that means there is a name like say a5 element, like a.2 element, like a root a 1.37, like that. And then I may be anything. I may be any abstract set. Now, how do you make this r to the power I as a module? Yes, we can make r to the power I as a module. Similar way. How do you add? Question of how do you add this thing? How do you add this thing? You just add component wise. So any element of r to the power I is just a function f, and another r to the power is another function is a g. So how do you add fg? F plus g is just a new function on r I, such that f plus gx is fx plus gx, and fx in r, gx in r, so fx plus gx in r in this ring, because r is a ring now. So we can similarly we can define the scalar multiple. F is an element of r to the power I. This is actually function. A into f is just, you can define a into f here. A into f is like that. It's taken on any value x. X is now in I. So it is a into fx. So fx is in r, because f is a function from I to r. X is in I. So a into r is defined. A into fx is defined in r. So, and this you can easily check the other condition of the module, and you can easily make that any r to the power I, r is a ring, as a module. So similarly, you can do it to the vector space also, but in the question of dimension is not finite. If I is infinite, it's a question of infinite dimension. So what is sum? Sum in the vector space, we also know it is what is sum. If there are two submodule, or two subspace pq, then p plus q defined like x plus y, where x is p and q, y is q. And sum of this is called sum of two submodule. Now, is the sum of two submodule is a submodule? Yes, sum of two submodule is again a submodule, like sum of two vector space is a subspace is a subspace. And you can easily check that. Take any two element x1 plus y1 and another x2 plus y2. Just add these two. It will be x1 plus x2 plus, because it is commutative. So x1 plus y1 plus x2 plus y2 is just using the commutative and associativity property, which is x1 plus x2 plus y1 plus y2. So x1 plus x2 in x, because in p, because p is submodule, and y1 plus y2 is q, because q is submodule. So it is x something element in q, p, and some element in q. So the addition and the sums would be in p plus q. So it is submodule. Similarly, the scalar multiplication. Again, if it is a family of submodule, it may be arbitrary, not only 2, 10, or maybe infinitely many, or maybe countably, uncountably many, any family of module, submodule. So p alpha is a family of submodule. Here is just only one, 2. So p1 is p and p2 is q, say. So just the index set has only 2 elements. Now index set may have several elements, it may be infinitely many elements like that. So then we define the addition like that. Now there is a question: how do we add this? We can like a coordinate system, but how do we add this? How do we add two sequences? Now this is the question, because if there are infinitely many, you can't just add, and then you can't have these properties of the submodule. So that's why we define like that. No, we don't define the sum as any element, just anything. You have to take such x alphas such that x alpha is 0 except for finitely many alpha. So finitely many alpha is non-zero. That means you actually sum of finitely any element. Your collection may be infinite. your set will be say P1, P2, dot, 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 countably many collection. But once you add this, you can't add like x1 plus x2 plus dot, 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 dot. You can't. There is a series. Then it's undefined. You can write this, but you can add this infinitely many element. Then if you want to add this, then it's question of limit, question of topology. But here no topology is now there. Here do not introduce any topology. Here do not introduce any distance or anything. So there is no question of limit or such thing. So we can't define the series. So we can define only a finite sum. So that means we need only finitely many alpha for which alpha x alpha is non-zero. That means if you say is a real number, say p alpha is all real numbers, say, and if you want to find this real number is a set of is a ring, and you want to make this r to the power infinity as a module, then what you'll do? You can't take any two element, say you can't take 1 plus 1 plus 1 plus 1. You just take some elements. Say x alpha, x1 is 1, x2 is 2, x3 is say minus 5, x4 is say pi, and then rest are 0. That means you need to add only finitely many elements. And with this addition, just is a submodule. Why you do not take this all non-negative, non-zero number? Because in that case the sum is not defined. In polynomial ring you just formally write that, but here you have to define what is the value exactly. What is it should be belongs to in R. In polynomial element is not in R. The set of any polynomial whose coefficient is in R in real number is not a real number. The polynomial is not a real number. But once we add this, that must be a real number. So you have to add this, and you can't take a series because no question of limit here. So you have to take the only finite element sum. We know how to add this, add two elements. So once we know how to add two elements, we know how to add 10 elements. We know how to add one core element, but we can't add a series. So that's why you have to take x alpha x0 except for finite many alphas for a family. Oh, obviously, if it is the family is finite, then no question of this thing. It is a finite, is okay. Now m and n can be thought as a submodule. How m and n can be thought as a submodule of product? Because it has only one element, but in P it's a coordinate system. Yes, you can do this like that. So any element in X, you can just think X is like x comma 0. And like I said, one-dimensional point is 1, but in a two-dimension, 1 is same as 1 comma 0. So is 1 is same as 1 comma 0? The answer is obviously is not, because it is said that two different set. 1 comma 0 is in R2, R cross R. But 1 is in R. How do it can be same? But we can thought this is called canonical isomorphism. It's called embedding. It's also called embedding. It's canonical isomorphism. We can think 1 comma 0 as a 1. Like in our geographical place in our Earth, we define a point as in a two-dimensional coordinate system, longitudinal latitude, but actually in a three-dimensional space. Actually, we just cut off the third dimension. The third dimension is the height. And we assume that the height is 0, is on the Earth surface. That's why we longitudinal latitude. We consider longitudinal latitude. But if you want to exact the position of in the space, we need a height also. So now the question: if the point in a plane, is it not a point in a space? Truly speaking, is not, because in a plane is just an R2. It can't be element of R3. But actually, we can think like that. 1 comma 1 position, actually 1 comma 1 comma 0. So that is a canonical isomorphism. So we can actually canonically isomorphic x with x comma 0, similarly y with 0 comma y. And with this identification, we identify. Once we get x in a p, we will say, okay, it is actually x comma 0, like a complex number and real number. So is real number is a complex number? Obviously. 2 is like a 2 comma 0, 2 plus I into I 0 I. Is I is not a complex number? Yes, I is actually just 0 comma 1. So that's why real number is an element of complex number. Actually, it's a complex number. But truly, if you say no, it is a complex number is R2 in R cross R. How can any element of R is a element of R2? Yes, the element in that sense, real number is not a complex number, but we can truly just canonically identify these two. So 1 like 1 comma 0. So if you identify that's 2, then your m, that m is not now x is in 0 comma x comma 0, now is a subset element of P. This is also element of P. Now this is element of P. Now this is submodule. Now m is a submodule. You can say, okay, how m is a submodule? M is not a subset of P at all, but we can think m as a subset identified after identification. And in that case, what happened? Your m intersection n must be 0 element, because your any element like x comma 0 and element like 0 comma y is only one element common there. Like in the real code, like complex system, the real line and the imaginary line intersect at only one point. Is only 0 point, 0 comma 0. Is a 0 element of P, is a 0 comma 0. In that case, we say it is a direct sum. And we write this. If I write this P equal to m, this big O plus n, that means two things. Number one, P is m plus n, a sum, and this sum is direct. M intersection n is only 0 element. Now there is again the question of internal external direct sum. There is it's easy. Actually, this is called external direct sum. Why? Because we take m and n are two different different module. M and n may not be from the same type of element. N may be, say, all real number, and n may be some dog, cat, cow, something like that. And there is a 0 element is called elephant. Now we identify one like 1 comma elephant. One elephant is a 0 element in n. 2 identify with 2 comma elephant, and tiger identified with 0 comma tiger. 0 is a 0 element of this our set. So now there are two different modules. Now if we just think like that, your Cartesian product is something like 1 comma elephant, 1 comma tiger, 2 comma cat, something. These elements are like that, and we can make this module. Now this module, now this set of real number, a set of these animals, that modules can be thought as identified with a submodule. This isomorphic canonical isomorphism through the canonical isomorphism. Now this direct sum is called external direct sum, because these two things are externally just adding two different sets. Now this may be so happen that there is a set, there is a real number, and we have two submodule of that. Maybe say Z is a ring, and two submodule is say 4Z and says 7Z. Now we can add the 4Z plus 7Z, and in that case 4Z plus 7Z, the intersection not 5, not 0. Is several other elements also there. 28 is there. But if it so happen there are two submodules, like a vector space, say x-axis and y-axis, two submodules, and they intersect only at the 0 point, then that direct sum is called internal direct sum. So actually the internal direct sum is like a two submodule is adding. External direct sum is something like, external direct sum is like external direct, is the same as external direct product. External direct sum and external direct product is a synonymous. Right? External direct product is something like there are two different sets. Now they are adding. Now adding through a common platform, in a common platform is after identification. Now once we identify, then we can think like a submodule. M and n are two different things. Now M is identified with m cross 0, m Cartesian product 0, and n is identified with 0 Cartesian n. Now m cross 0 and 0 cross n is the submodule of P. P is m cross n. Now in that case, this is just an internal direct sum. So this internal and external is just merely is a terminology. You can think is the same thing. Internal external is not actually different. The external direct sum you can think like an internal direct sum also after this identification. But some in literature they use internal direct sum when their submodule already is given under a module, and external when there are two different modules come from the different set or different objects. But we can think external direct product and external direct sum is same, like internal direct sum. So actually there are two things, sum and direct sum. Some in the sum that may not be direct. The intersection may not be more than 0 element, maybe other than non-zero element there. But once it is direct, then 0 is the only element in intersection. But obviously, once it is a external, that must be direct. But when it is internal, maybe may or may not be direct. And your external direction can be think as an internal direction after this identification. So actually, there are two things, two concepts, sum and direction. So now there's a very important thing like a vector space. We know if M or N is a submodule like a subspace, then the sum is direct if and only if the elements of Z can be written uniquely as like that. You know this. This if it is a direct, then this representation is unique. Why? So it's okay. You have two representation, or you say this. I have one more representation. Is that unique? Is there x1 equal to x2, y1 equal to y2? Yes, because x1 plus y1 is actually x2 plus y2. Just you take the side chain. Your x1 plus minus x2 is equal to is equal to just y2 plus minus y1. But this is in n m, and this is in n. Now, if two elements are equal and two elements, one is m, the other is m, so what? This is the only zero element only is there because it's direct. So zero is only the zero element is this. So if it is zero, so x1 equal to x2, y1 equal to y2. So if it is direct sum, then representation is unique, and you can easily check the converse also. If this representation is unique, then the sum must be direct. Contrapositive way, you can say if the sum is not direct, then you can always have two different representation. If there are any other than 0, there is an element, non-zero element, say in M, that element in M also and N also, you can represent in the two different way. That say A is in M and A is in N also, and A is not equal to 0. You can write that A like that, 0 plus A, again it is A plus 0. Two different representation. Now A is in M and A is in N, and here A is in N, 0 is in M and A is in N, and here A is in M and 0 is in N. So, but A is not equal to 0. So two different representation. But if it's a direct, you can't do this. Now, same thing in vector space also. This is, we know this direct sum actually is like an independent thing. If they're independent, if vectors are independent, then the representation is unique. Now, direct sum of family of submodule, same thing. Like the family is maybe finite, maybe infinite, countable, uncountable. And again, this sum, we know how to define this sum. Obviously, this sum, this exercise, that means alpha, x alpha means this finite for x alpha is 0 except many finitely many alphas. So this sum is actually always is finite. This sum is in a vector space also. We know the if vector space have many elements, it's infinitely many elements, but the linear combination of a element from the element of vector space is just a finite linear combination. Linear combination means it is finite. So this sum is always a finite. It is alpha is I. Alpha can take any I, but x alpha is only finitely many is at 0 or non-zero. So, and this representation must be unique. Similarly, you can prove this because it is finite. If it is infinite, there is a problem. Since it is finite, you just say one expression there are 10 elements, another expression says 20 elements. So 10, 20 maybe may not be different from the same submodule in the same fact P alpha. So there are 30 manys, and you can just take because they are all the intersections are 0. P alpha and intersection P beta is 0. Only one element. So and using that you can easily show. Now there is a very good question. This now what do you mean by this and what do you mean by this? This is just this is not a finite thing. It's like a sequence. So if I write product n equal to 1 to infinity R, that means is actually R here Rn is actually R. So R maybe say real number, say. Now this is a set of sequence. This is a set of sequence. But if I write this R n or just Rn equal to R, n equal to 1 to infinity, this is set of polynomials. This is set of all sequence, but only finitely many elements are non-zero. So by definition, for this product is you can take anything. So the direct product is now different from the direct sum. And this direct product is a submodule. The direct product is a submodule. You see this in the first slide. This is a submodule, but this submodule and this are different because this is superset. And it can be equal. Yes, it can be equal if I is finite. If I is finite, actually this is the same concept. This is just finite sum. No question of infinite sum. So that means this is a module. This is a module. Clear? Remember, this is the external thing. So this is the module. Right hand side is a module. Left hand side is also a module. But this may not be equal. This is a submodule. If I is finite, obviously they are equal. Is clear. If I is not finite, say it is a set of all integers. Then this is actually collection of all series, or maybe all formal series. That means all sequence, and this is a collection of all polynomials. Formal notation. That means it's a set of all finite, like a finite sequence. That means it's a sequence. Okay, it's a sequence, but there are only finitely many elements are non-zero. So now we are in the end. There is called direct summand. If P is a submodule, P is a module, and P is a submodule of module M. So P is a submodule. Then we call it the direct summand or just summand if you have another submodule Q of M such that P direct sum Q is M. So this is like a complement. In vector space, like a complement. Is a complement. You know what is called complement. So here it is called supplement. In module, we call Q is called supplement of P. In vector space, we know it is a complement. We call it as a complement. So in vector space, we call complement. Here is supplement. Same thing actually. So that means this sum is direct. And a summand need not be a summand. And that's the important thing. Now we have an idea of why these modules are different from the vector space. In vector space, every subspace is a summand. So if you have a vector space V and you have a subspace W, then always if let's say it is a finite dimensional vector space, then there is always it's called complement thing, or maybe orthogonal complement in inner product space, or maybe a complement part, which is V. If it is orthogonal, this is called orthogonal complement, you know. But interestingly, for module, it may not be happen. So if 2Z is a submodule of Z, we know 2Z is a submodule of Z. But there is no other submodule, just 2Z direct sum with some module is give this. No, such a submodule does not exist. Does not exist. Because in that case you need one, and once you need one, actually 2 is there, so it can't be direct. You need one basically. So to right hand side 1 is there, left hand side there is no 1, so 0 plus you need 1 or maybe minus 1. At least one odd number must be there, and once one odd number is there, that odd number plus odd number is actually the even number, so it can't be a direct. So in module, submodule may not have this criteria, this property, but vector space has this. Also, if supplement exists, it here is not exist, but if it exists, that may not be unique. That is also in vector space the same thing. If they like I say to R2, if this is a say R is a one, say W, and we have a one, this is say one complement, another complement like that. Say this green part is also another complement. You know, this is another complement. Any line which is not this line passing through the origins, these are all complement of W. If you add this to this W and the red one is gives R2 with W, and this green one, this also gives the W R2, and W plus this plus means a direct sum. The black is also is R2. So this is all, this criteria is in vector space. The interesting thing is this is not in the vector space. This is the different thing from the vector space. Now some analogy. Analogy is clear now. What is the analogy between the vector space and module? The linear span actually say existence of the linear combination. We know that. So if there is a vector, some alpha 1, alpha 2, alpha n, and this is a span of this vector, then any element in any vectors is belongs to span. We know there exist C1, C2, Cn scalar or in the field, such that C1 alpha 1 plus C2 alpha n Cn alpha n is actually V. So V can be written as this linear combination. Again, if it's a infinite alpha 1 alpha alpha n infinite, then also there are finite, sum is finite by definition, by the definition of linear span. Now existence is actually existence. And what is independency? Independency actually says the uniqueness of the linear combination. So if it is independent, then if it's a vector in the, say, alpha 1 alpha 2 are independent, if V is not in the span, then you can't write. But if V in the span, then you can write that because in the span, and this dependence is unique. Now the same idea here is sum, and sum is actually the existence, and direct sum says the uniqueness. And this sum and direct sum concept is vector space also. In the vector space also sum and direct sum. Actually sum means you say okay in a linear span. So the sum means the existence of the some linear combination. And direct sum is actually say that this linear combination is unique. So module also same thing, same idea. If it is a sum of two or many sum module, then any element of that sum can be written the sum of element of the sum module. And if this sum is direct, then this representation is unique. It's like independency. So direct is actually same concept like independency, and sum is actually concept like dependent. Span. So this is the analogy with vector space and module, and this is the end of lecture 3. And there is one more reference, commutative algebra, Gopal Krishnan, this Oxonian Press Private Limited. So I stop here. We free module we will say discuss in the next class.